Alrighty. So in this lecture, we're going to be determining the moment of inertia of a spherical shell, which is pretty much just a hollow sphere. So first, let's think about the moment of inertia equation and remind ourselves what it is. It basically says that the moment of inertia I is equal to mass of a point times its radius squared. Well, in calculus, we can just say a whole bunch of point masses added up is equal to the total moment of inertia. So the total moment of inertia is equal to the integral of the radius squared, because the radius is an interchange, but we're going to say dm because it's a segment of mass, not actually the region's total mass. So now let's relate this to a sphere. Well, first of all, let's think about where we place this axis of rotation through a sphere, how it's going to affect the moment of inertia. Well, by thinking about symmetry, we can actually determine that the moment of inertia of a sphere, as long as it's placed through the center of mass of a sphere, or the center point of a sphere, is actually going to remain the same. So regardless if we place the axis of rotation right here, assuming it goes to the center, right here, assuming it goes to the center, it's all going to be the same, because if we're thinking about symmetry, it's still going to have are still going to look the exact same regardless of where you decide to locate your axis or your axis of rotation. So we have our center point, and we're going to make the axis of rotation go right through here, just for simplicity's sake. And we're going to just go ahead and label this axis the x-axis. And we can go ahead and label another axis. We can say this is the y-axis, just to make things easier. Now let's think about the qualities of a sphere. From the center point of the sphere out to anywhere on the sphere, the radius is going to be equal to r. And this r is not going to be the distance between our axis of rotation. Instead, we can think about the distance between a segment of the sphere on different points of the x-axis, because that's where they're going to have pretty much the closest regions to our axis of rotation is by thinking about points along the x-axis. And let's say the distance between any point x is going to be a changing value of little r. And it's going to depend along the x-axis what the radius is going to be. But the radius is going to account for all of the sphere, so it's going to go up and around. And each little section is going to have a distance r. All right. Now, let's actually draw this out in a little bit more of a 2D space. We're going to say that we have an x and a y axis. We're going to draw a circle. We have our x and our y. And now we have big R and a little r. Now, what we're going to actually want to do is make a function of r. And how we're gonna do this is basically, or why we're gonna do this is we want to know what are different radiuses of our different sections of mass. So, yeah. So pretty much we're gonna try to find out an equation that can give us our radius squared in terms of actually a theta. And how we're gonna do this is we're gonna say, okay, sine of theta is equal to little r over big R. And there's a simple multiplication. We can get r sine theta is equal to r. And we can actually plug this directly into our moment of inertia equation. So we're going to get r sine theta squared dm. Now that we have a little function that tells us what our different radius is going to be for each little segment of mass, we actually need to figure out what the mass is for each little individual segment. So the dm for each individual segment. And what do we know about dm? Well, dm is a section of mass, so it's actually going to be dA, which is a segment of area, times density. And now you may be thinking, a sphere is a volume, right? Well, not in this case. It's a hollow sphere, so it's actually more like a surface area rather than a volume. It's going to have density based on a surface area. So what is the density of a hollow sphere? Well, we know that density is equal to mass over area in this case. And mass is going to be the same, but our area is actually going to come from our sphere's area, which is actually going to be mass over 4 pi, the radius of the circle, or of the sphere, squared. So now that we have our density, now we need our dA. And for our dA, we're going to go back up here, and we're going to think about each little segment. Now, we're looking for the area. And this is pretty much going to be almost like a little rectangle, because you have to remember this is infinitely small, so the curves are going to begin not to exist. Well, our length, our pretty much our circumference, because you have to remember it goes around and it's going to be a complete circle, is actually going to be 2 pi r. 2 pi little r, because it really does depend on which point or which x point you're looking at. So r is going to be a function. It's going to change. So it's equal to 2 pi r. Now let's see what our length, our width is going to be. How much this little section is going to be wide. And how we're going to think about this is actually using something that we learned back in Math 172, or pre-calc trig. We're going to think about a circle. So the same circle we were thinking about earlier, right? We have our little, we'll say we have our little mass section right here. And then we have our center point on x and y axis. Well, in pre-calc trig, we learned that the arc length of a circle is equal to theta multiplied by the radius. Well, for each individual point, it's going to have an infinitely small theta rotation between the first point, or the beginning of the line segment, and the end of the line segment. So we can actually write that as S is equal to d theta r. So this brings our total equation to dA is equal to 2 pi r times d theta r. And now we can actually go ahead and plug in our value for r earlier. So 2 pi times, and we're going to plug this in, r sine theta times r times d theta. Okay. Now that we're able to find our dA and our moment of inertia, we can plug it direct, or now that we have our moment of inertia and our dA, now we can solve for dm. So dm is equal to dA times density. So dm is equal to 2 pi, and then we're going to combine like terms, r squared sine of theta d theta multiplied by mass over 4 pi r squared. And we're going to cancel out terms again. So dm is going to be equal to 1/2 sine of theta d theta. And now we can plug this whole entire expression into our original moment of inertia equation. So I is going to be equal to the integral. And now that we know that it's going to be d theta, we can actually think about what bounds we're integrating this from. And it's going to be from 0 to 180. But we're going to think about this in radians terms. So it's going to be 0 to pi of r sine theta squared multiplied by 1/2 mass sine of theta d theta. Alright, now we can go ahead and combine some like terms and pull out our constants to the side. So it's going to be the integral from 0 to pi. And we can go ahead and pull out our m over 2. And we can distribute r squared, so it's going to be r squared sine squared theta times sine of theta d theta. And we can actually say this is equal to, remember our r squared is actually a constant too. So it's going to be mr squared, because the radius of the sphere is never changing, from 0 to pi of sine cubed of theta d theta. And now the rest of this problem is going to be some pretty basic integration. It's actually going to use the problem. But first we have to do some trigonometric identities. So this is going to be mass times radius squared over 2 times 0 to pi. And we're going to want to separate one of these signs out. So it's going to be sine squared theta times sine of theta. And then we can use a trig identity, our Pythagorean identity. So write this is 1 minus cosine squared theta sine of theta. And now we need to do a u substitution from here. So u is equal to cosine of theta. Du is equal to negative sine theta d theta. So du over negative sine theta is equal to d theta. And we can plug this in. So negative mass radius squared over 2 times the integral 1 minus u squared is going to be du. We also need to change our bounds of integration. So 0 to pi cosine of 0 is going to be positive 1. Cosine of pi is going to be negative 1. And then we can actually use our integration laws to rewrite this as the positive, our positive mr squared over 2 integral from negative 1 to 1 of 1 minus u squared du. And then here it's just a basic integration, so this is going to be mass times the radius squared over 2 times u minus u cubed over 3 evaluated from u is equal to negative 1 to 1. Now if we plug this in, it's going to be equal to mass times the radius squared over 2 of u minus 1, or sorry, not u, 1 minus 1/3 minus negative 1. And that turns into plus 1/3. And this turns into negative 2/3 minus, and this turns into positive 2/3 times mass radius squared over 2. And now this turns into I is equal to mass times the radius squared over 2 times 4/3. We can divide out our 2 and we get I is equal to 2/3 mass times radius squared. So the moment of inertia of a spherical shell is going to be 2/3 mass times your radius squared. Now that we went through this whole entire process of finding the moment of inertia of a spherical shell, you may be asking, how is this useful? Well, it's useful for hollow shells, of course, but more specifically, it's going to be useful to finding the total moment of inertia of a completely normal sphere. Because you see, a completely normal sphere actually, or a solid sphere, is going to be just a whole bunch of spherical shells with a varying radii. So, to find the mass of a solid sphere, or not the mass, but the moment of inertia of a solid sphere, it's actually going to be equal to the integral. So adding all of the small spherical shell moment of inertias with varying radii. So it's actually going to be 2/3 mass times radius squared dr. And the radius, or sorry, it's going to be dr capital from 0 to a constant, whatever your spherical, or whatever your solid sphere is going to be, because you're adding up all of the small spherical shell moment of inertias. So that's what we're going to do going forward, and especially in some application problems. But thank you all for your time, and I hope you enjoyed learning about the moment of inertia of a spherical shell.